This is section 9.5, alternating series. Yes, I am. 9.5. Yeah. Although we are way ahead of the game. This Wednesday, this Thursday, is the halfway mark for the semester. So could be. That's what Visa was telling me, so I don't know. I don't necessarily trust Visa. Alternating series test, theorem 9.14 says let a sub n be greater than 0, the alternating series. The summation from n equals 1 to infinity of -1 to the n power a sub n, and summation n equals 1 to infinity of -1 to the n plus 1 a sub n converge when these two conditions are met. When the limit as n goes to infinity of a sub n is equal to 0, and when a sub n plus 1 is less than or equal to a sub n for all n. Okay. Oops. There you go. Okay, so let's take a look at this problem. N equals 1, -1 to the n plus 1 over n plus 1. And the instructions say determine the convergence or divergence of the series. Now, if I back up to here, you notice they got the -1 to a power separate. So I can bring it out in front here. And then I'd have 1 over n plus 1. Now, based upon our definition, when you have that separate like that, your a sub n is whatever follows it.
Okay, so that would be the 1 over n plus 1.
Exactly. And so then, two criteria has to be true. The first one, the limit as n goes to infinity of a sub n has to equal 0. So we got the limit as n goes to infinity of 1 over n plus 1. And although it's not exactly just plugging it in, we're evaluating as it gets closer, but if you were to think of it plugging it in, infinity plus 1 is infinity, 1 over infinity is 0. So that's our first condition met. Second one is that a sub n plus 1 has to be less than or equal to a sub n for all n. Well, if I were to take this n plus 1 and plug it in for the n here, I'm going to have 1 over n plus 1 plus 1. And this is a question mark. We're wondering if that's true. And then 1 over n plus 1.
I think that would make sense because if you keep on increasing the bottom, it's going to get smaller.
Right. So this will always be smaller over here, won't it?
Yeah.
So yeah, that's met also then. So since both those are met, it says it converges. wouldn't bother me. I've had people that come in and eat corn nuts, so. And the school actually put it in the freaking machine. It's like, what are you doing? I was trying. I mean, those are the worst things in the world. We're chewing ice. That's funny. And I like to chew ice myself, but you don't realize it when you're chewing ice how loud it sounds to everybody else. Okay. I'm gonna go ahead and put the -1 to the n power to the side because I know it's got to be there. And then I got 1 over 3 to the n. Now, if you have that to the side, this is always your a sub n. And again, we need to check these two criteria. So we're looking at the limit as n goes to infinity of a sub n, or the limit as n goes to infinity of 1 over 3 to the n. Now, if I had an n down here, I'd have infinity, of course. If I have 3 to the n, it's just going there faster, isn't it? So that's going to give us 0. So that criteria is met. Second criteria is this check right here. A sub n plus 1 has got to be less than or equal to a sub n. If I were to plug in n plus 1 in for the n, specifically into the a sub n here, I'm going to have 1 over 3 to the n plus 1. And this will be 1 over 3 to the n. Now that I can rewrite as 3 to the n times 3 to the first. And I could factor that 1/3 out. Now what happens, these are both the same, they're 1 over 3 to the n. What happens when you multiply one side by a fraction? It becomes smaller. So that would be true then. So the answer on both of those is true, which means it converges. Mm-hmm.
How did you get 3n
Going backwards, if you have 3 to the power times 3 to the power, you add the exponents together. And so that's why you get this. Going the reverse direction, you can always read it as multiplication. Or do you mean this n plus 1 here?
like that. Like,
oh, you just plug in n plus 1 for the n.
I know, but last time we had
It had another number there.
plus 1.
Yeah, ours here just has an n.
Okay.
Yeah, the one we had before that had like n plus 1. That's why we did that. Okay. One. Oh, Okay, so this is our a sub n. Again, the -1 to the power you just put out in front right there. And we got two criteria need to be met. One of them is the limit as n goes to infinity of a sub n of n minus 1 for n plus 1. What rule would I use there? There is one that would take ln. It's just totally bizarre. Whether I actually do it correct or not, I don't know. We'll go to CalChat if I can. But this one, you could take L'Hopital. Did you say L'Hopital's rule? Oh boy, my hearing's bad. Sorry about that. I thought you said ln. So L'Hopital's rule, yeah. That gives us 5/4. Now that's not obviously not 0, is it? Which means that test can't tell us anything. And in terms of that, because just because it doesn't, you see, it says converges when these two conditions are met. It doesn't say it diverges if they're not, does it? That's an important distinction. I put a little note on this so I could look at the formula. Notice how I put nth term test. These are all summarized in the book over here on page 636. This is probably the best table to have handy. And over here, for the nth term, it says the limit as n goes to infinity of a sub n is not equal to 0. And that's a condition of divergence. So by this nth term test, this diverges. Okay, let's take a look at this one. And I forgot. Take the -1 to the power out in front. So we got 1 over square root of n. And yeah, two conditions. Limit as n goes to infinity. This is our a sub n. So 1 over square root of n. Now, even though there's a square root on it, what's it still going to go to?
I mean, if it's infinity, it's still not 1.
Bigger on the bottom, which then goes to 0. So that condition's met. Yeah, it just won't go there as fast. That's the only thing the square root does, is delays it a little bit before it goes to 0. 2, check that. A sub n plus 1 is less than or equal to a sub n. So we'll plug in n plus 1 for the n. Now I have 1 over square root of n plus 1. This will be 1 over the square root of n. And if I think about it, even though the square roots are here, it really doesn't mean anything. Because if I were to put in like a number, 9 plus 1, that gives me 10, and this would be a 9. So this is going to be what? Smaller. Yeah, square root doesn't really affect that. So since both of those are true, it converges. Okay, let's take a look at this one. 19. F1 to the n plus 1. N plus 1 over the natural log of n plus 1. And this is our a sub n. So limit as n goes to infinity of a sub n. If I took like each one of those separately, both the top and bottom would go to what? Yeah, so we can use L'Hopital's rule again. Derivative of n plus 1 is 1. The derivative of natural log of n plus 1 is 1 over n plus 1 times the derivative, what's inside the parentheses, with respect to n. But the derivative of n plus 1 is 1. And you flip this, multiply times the top, and that gives us n plus 1 over 1, or just n plus 1. And then if I were to study it as it goes to infinity, it goes to what? Infinity. Now, that causes our, where in the world is it? That causes this to fail. That doesn't mean it diverges, though. And that's why if you look in the explanation, they'll go on to explore another technique, and this one is the nth term test. So the nth term test says since it's not equal to 0, that's our condition of divergence. So that means it diverges.
Question. Whenever we take the test, most likely we would have something like this. We would have to have a table as well.
I would have this. Because I'll give you a little hints like this on test. And I'll say determine the convergence or divergence using the alternate, what was it called? Alternating series test. And then I'll put a little note in here like L'Hopital. I may not say L'Hopital, but I say then use an nth term to guide you. But I won't tell you whether it converges or diverges. So you need to have that written down so you can look up that formula, that rule, and see what it says. And I can't give this to you because it prints this really nasty thing when I print it off, like you'll be prosecuted if you give this to anybody. This is probably your best summarization of that. It's on this page. Looks like a lot, but if you try to combine all those slides I gave you, then it'll be more than that. Okay, let's take a look at this one. Okay, number 23. Now that is a good point what you just said. Because our rule actually says, I think, n equals 1. So the question becomes, what's happening at n equals 0? Well, if I plug 0 in, that's going to be negative 1 to the 0, which is 1. If I plug 0 in here, does anybody know what 0 factorial is? It's 1. So 1 over 1 is 1 times 1 is 1. 1 times anything doesn't actually change anything, does it? Or no plus. Sorry, plus that. Well, would that change it? No, because still you're wondering what's happening over here as it goes to infinity. Is it going to 0, for example? Okay, so the fact it starts at 0 won't affect the test. Okay, so this is our a sub n. Limit as n goes to infinity, 1 over n factorial. Now, if I think of just plugging infinity in, I'd have 1 over infinity, which is 0. Infinity factorial goes to infinity even faster, doesn't it? Exactly. So this would be 0, so that's met. We're wondering if a sub n plus 1 is less than or equal to a sub n. If I plug n plus 1 in, I'm going to have 1 over n plus 1 factorial. Okay, so this means 1 times 2 all the way up to n times n plus 1. This one is 1 times 2 all the way up to n. Now, there's different ways you could think of this. You could just look at it and kind of think it through. You could multiply both sides by 1 times 2 all the way up to n, and you'd be left with 1 over n plus 1 is less than or equal to 1 over 1. And when I plug in more n's, this becomes bigger. This is always 1, isn't it? So it's definitely less than or equal to. So it's however you want to think of it. Now the question becomes, does that n equals 0 really affect it? Well, if I plug in, if I look at these right here, just to verify, it should be okay since we did sub n's and not actual numbers. But if I were to plug that 0 in, 0 plus 1 is 1. Put 0 here, that's a sub 0. If you put these in, that'll be 1 over 1 factorial. This would be 1 over 0 factorial. Both of those give you 1, doesn't it? Which is still true, less than or equal to 0. So it hadn't been violated, the fact that it started at 0. So yeah, since both of those are true, it converges. I'm not very good at rewriting those. This book hasn't really focused on that too much, which is good. The original problem. Like this right here, if you're good at it, you can rewrite in this manner. Yeah, and this would be, if I plugged in 0, that'd be a 0, so this would be n minus 1. Let me think. 1 minus 1 is 0. That'd be the same as that. Okay. Now here, I'm guessing it's either n plus 1 and n minus 1. Maybe it doesn't matter. Let me see. If I plugged in 0 here, that'd be negative 1 to the 0. If I plug that in, I want it to be 0, so it'd be. But then that violates, because we don't say anything about. Maybe you can't rewrite it then. On that one, anyway. Let's see. This talks about alternating series remainder, and I'm not going to show any problems on this, but it says if a convergent alternating series satisfies the condition a sub n plus 1 is less than or equal to a, then the absolute value of the remainder, r sub m, involved in approximating the sum s by s sub n, is less than or equal to the first neglected term, that is, the absolute value of s minus s sub n is equal to r absolute value of r sub n, which is less than or equal to a sub big N plus 1. And I don't think it has a whole lot of purpose, to be honest. But they throw a couple problems in the book involving it. So don't worry about that. Now, theorem 9.16 says if the series, the sum of the absolute value of a sub n converges, then the series, the summation of a sub n also converges. And definitions of absolute and conditional convergence. The series summation of a sub n is absolutely convergent when the summation of the absolute value of a sub n converges. And the series, the summation of a sub n is conditionally convergent when the summation of a sub n converges, but the summation of the absolute value of a sub n diverges. What in the world does that mean? Let's take a look at this one. Okay, instructions say determine whether the series converges absolutely or conditionally or diverges. And at some point in time, we'll have to use this fact, convergent geometric series. Hopefully it's on this page. Yep, here's the geometric series. Okay, so let's take a look. On this one, yes. But they're wanting us to check these definitions. So, yeah, that's a good point. Some of these you can use. You're not restricted just to one technique. You may find two techniques to work on. Okay. Now this doesn't say anything about the -1 being pulled out, does it? So if we look at the absolute value, that right there, what happens to a -1 to any power? You can take the absolute value of it. Yeah, it always disappears. Now 2 to the n power, assuming n starts at 1 and goes up, even if it didn't start it, will 2 to the n ever give you a negative number? No. So I can drop that. Now remember the form of this. We have a r to the n power. No, you can actually rewrite the 1 as 1 to the n power. And now since the top is the n power, the bottom is to the n power, we can rewrite this as 1/2 to the n power. It is proper algebra to rewrite that as 2 to the -n power. That's a good thought, but the fact is on this, our n has to be can't be negative. So then our r, according to that, will be 1/2 1. And it says if the absolute value of r is less than 1, that it converges. Okay, so we just said that the summation of the absolute value of a sub n converges, didn't we? So that means that our series without the absolute value is absolutely convergent. Now, the other one that's conditionally convergent is when our summation of a sub n converges, but then the absolute value diverges. So, okay, let's take a look at, are those the same? Guess we won't look at that one then. Okay. They're not hard. The absolute value always gets rid of the -1 to a power, and then you're left with this, and you just have to rewrite it to look like something in here. That's probably the challenging part. At least when I took Calc 2 way back when, trying to figure out which one to reuse, which one to rewrite that was the hard part. Okay, that's 9.5. Okay, 9.6. This is the, actually, let me stop the video and start recording again. What was that? 9.5. Alternating series.